Okay, we're going to continue today discussing more graphs and displays that you can use with your statistical data, mainly stem leaf plots, dot plots, pie charts, Pareto charts, and time series where you have a scatter plot and you do a line of best fit with paired data. So we're going to start off with stem and leaf plots. So a stem and leaf plot would have a stem and a leaf. Leaves are one digit. So if you have two-digit numbers like we have here, the stem is going to be a tens place and the leaf is going to be ones place. So it's possible to have a 0 for a stem if you had numbers that are less than 10. Okay, so here is a big stem plot. You want to assign a key. So you just kind of write your key by saying, well, 4/9 equals 49. So it's telling you how you would place that number 49. So 4 would be in the stem and 9 would be in a leaf. So you kind of go through your text messages and you just write them down in whichever plot they need to be in. So we kind of go through it. It's 7/6, 120, 12/2, 6/6, 7/6, and so on. Fill that in. And then you need to go back and put them in numerical order. So the final stem plot should look like this. Okay, so we have 16, 19, 20, 23, 24, and so on. So your leaves should be in numerical order, not so much how they came in the data that you got. Okay, so you should always order your data because most charts it needs to be in order. Okay, so if you're looking at this, these are the number of text messages sent. You can see the bulk of them are between 20 and 80. So an interpretation could be at least half of them are between 20 and 50 even. Okay, but you have kind of the slowing down here in the 90s and above. So there's different interpretations you can have. Those are just observations. So a dot plot, just like the stem and leaf plot, every single data point is shown separately. A little bit more complicated because you have to have that number line that encompasses all of the points. You can see where they're estimated. Dot plots are nice because you can quickly see groups, like with a stem and leaf plot. You can quickly see your modes. You can see the high points here. Okay. So 29 and looks like 33 would be modes, bimodal, okay? And you can see, how it's spread out. Okay. But if you count the number of dots, you'd have the number of data entries. They're all shown separately, both of those graphs. So a pie chart, you've seen pie charts before. It's a very convenient way to represent qualitative data as percents of a whole. We divide them into sectors, 360 degrees, divided into sectors. The area of each sector is proportional to the frequency of each category. So how do we do that? Here's some data. The number of degrees earned conferred in thousands in the 2014 are shown in the table. Use the pie chart to organize the data. So you need to figure out the relative frequency. So relative frequency is the frequency divided by the total number in the data set. So about 26% got an associate's degree. And if we wanted to get a central angle, we would multiply that by 360. And I'm rounding to the nearest degree, so 95 degrees. Okay, so 1,870 divided by 3,805 would give me a relative frequency of 0.49 or 49%. And again, you multiply that by 360 to get the degrees, and so on and so on. Okay? So your relative frequency should add up to a 1. Your central angles should add up to 360. So if we look on the next slide, we have that chart filled in. Then you would get your protractor out, get a circle drawn, and use your protractor to get your angles. This is what this pie chart would look like. And that's something you just need to practice with the tools. Okay, so you can see very quickly almost half got a bachelor's degree. Okay, a small section got a doctorate's degree. And associates and masters are pretty much the same there. Okay. Associates being a little bit bigger, but they're splitting the other ones. Okay. So a Pareto chart is like a bar graph. The bars do not touch, and they're positioned in decreasing height. So the tallest one is on the left, and they decrease from there. So that's what's important about the Pareto chart that makes it different from a bar graph. A bar graph, they can go in any order. When it's in a Pareto chart, it starts with the highest frequency and decreases. Okay? So those are fairly easy to see. So we have in 2014 the leading causes of death in the U.S. were accidents, cancer, chronic lower respiratory disease, heart disease, and stroke. So the Pareto chart would start with heart disease because it's the highest frequency. Then it would go to cancer, then to chronic lower respiratory disease, accidents, and then ending with stroke. So that's what it would kind of look like. Okay, so you want to just graph those frequencies. Deaths in thousands, but we want to start with the highest frequency and then decrease from there. They're fairly easy to draw. Okay. So when you have paired data, you have an X and a Y. You're doing a correlation between, in this case, IQ and income. And you want to try to see if you have a correlation. And here it looks like you can see some positive trend here. The higher the IQ, the higher the income. But it's not an exact trend. That almost looks like instead of linear, it might be quadratic, but you'd have to get into calculations for that. But you can see the scatter plot. Okay, two-dimensional. So here's one by a British statistician, Ronald Fisher, and he was famous for this iris data set, measuring the lengths of petals and the petal width for different species of iris, and he came up with this correlation. So you can kind of see as the petal length increases, well, then the petal width would also have to increase. Okay? You can kind of see that it's a positive trend. As one goes up, the other one also goes up. All right? So if we're going to do a time series chart, time is always your x-axis. And we're just doing the motor vehicles in this case. So the burglaries, separate situation. So if I'm just putting the motor vehicles in a graph, your y-axis is going by tens. So, make sure you're spreading that out and making it at least by every other one. You don't want it to get all bunched up. You want to be able to see some correlation here. So you can see the decrease in accidents, and then it seems to level off. So there just seemed to be a decrease in accidents until year about 2000, 2010, it starts leveling off. So that would be an observation or a pattern that you can see. Okay? Well, I guess it's motor vehicle thefts. I was thinking it was accidents. All right, so we're talking about thefts. All right, so here's some practice questions. Let's match the plot with the description of the sample. So times in minutes it takes for a sample of employees to drive to work. Well, which one of those looks like times that you would drive to work? And this would be in minutes. I would think it would be this guy right here, the first one, the first dot plot. So you could have a 5-minute drive to work. You could have a 38-minute drive to work. Okay. Up here, everybody's drive to work would be over an hour, which isn't realistic. and certainly not over, 200 minutes, which would be over 3 hours, okay? Nor would it be 8 to 4 minutes. Grade point averages. So that would be perfect for this one here. If you're looking at between 0 and 4 points. Top speeds in miles per hour for high performance sports cars. So you're talking top speeds. Well, speed isn't going to be 67 miles per hour. A top speed of 205 miles per hour would be more realistic. And the ages and years of residents in a retirement home, that looks like this group, 60s and above. Okay? Explain why the graph is misleading. So if I'm looking at the first graph here, I can see a huge mistake. Even though it looks really nice and neat and it looks like a Pareto chart, the problem is this right here. They have taken the y-axis and done one of those little jogs saying, we're not starting at 0. You need to start at 0 on your y-axis because that shows you something. Here, the differences between the third and the second quarter look significant. But in reality, if you look, it's going from 105 to 120. That's only $15,000. In the big scheme of things for a company, $15,000 is not significant at all. But because they started the graph here at, let's say 80, you can't really see that it's not significant. They've narrowed your focus down so that looks like a big, big difference, and it's not. The second one, if you're looking at the chart again, cute little way to do your bar graphs. It's original, very cute little crude oil drums, but you can't make a big oil drum. When you have it this much larger, it makes it look again like a significantly larger outcome, and it's not. We're looking at, not even 500,000, or I'm sorry, 500 million. Again, it's not real big. This distance here is what's important. But they made that drum so big, it makes it look like it's a bigger difference than it is. Okay? So it can be misleading. Okay, the oil drums have to be the same size. Okay, so this is a back-to-back stem plot. So you have the same stem, but your leaves are going in opposite directions. So the minimum value for law firm A is here. The minimum value would be 9D. And it's in thousands. So $90,000 is the minimum for law firm A. Okay? So back-to-back stem plots is really nice to compare two similar sets of data. Okay, and we will see you tomorrow.